Hey there, it's Shannon Magic Myers coming at you live from San Diego, California. All right, logical form and logical equivalence. The central concept of deductive logic is the concept of argument form. An argument is a sequence of statements aimed at demonstrating the truth of an assertion. The assertion at the end of the sequence is called the conclusion. And the preceding statements are called premises. For example, the following sentence reads, if Shannon creates video lectures for her online classes, then her online students will be more successful. So if we just look at this as what is the premise, what is the conclusion, we've got this one premise here, right? This is a premise. And then this, so Shannon creates video lectures for her online classes. That part's the premise. Her online students will be more successful. That is the conclusion. So I'm not speaking to the, truth or validity or, anything like that. This is just a very simple, what's a premise, what's a conclusion, okay? For the common form, we would let P represent or denote is what I commonly use. The portion that says Shannon creates video lectures for her online classes. And if we let Q denote her online students will be more successful, we have a statement that reads, if P, then Q. Cool so far? Awesome. All right, well, I just spoke the word statement. So in mathematical theory, new terms are defined by using those that have been previously defined. Since this is a recursive way of defining terms, we need to start by using initial terms, which remain undefined. So we're kind of taking this on faith. In logic, these terms are the words sentence, true, and false. So our first official definition, a statement, which is also called a proposition, is a sentence that is true or false, but not both. So let's check that out. Let's determine if these sentences below are statements. An iPhone is an Apple product. Well, what do you think? This is a sentence, correct? Good. And is it true? Yes. Right? So this is a true sentence, which would make it a Good. Statement by definition. Now, an iPhone uses an Android operating system. Again, this is a sentence, but it's false, right? iPhones use iOS, not Android. So this is a false sentence. So we still have a statement. Meets the definition. Alrighty. She has an iPhone. What do you think? It's a sentence, right? That is true. But who is she, right? Depending on the she one is referring to, this could be true or false. So we don't know. So we would not call this a statement that we'd use in an argument because it's not defined enough. All right? Compound statements. We would be very limited if all we used were single statements and arguments. Below are 3 symbols used to build. So we're going to be building logical expressions. So we build more complicated logical expressions out of simpler ones, just like your, regular word problems. You first learn about phrases, like mathematical phrases, and then you put them together to model applications. So here, we're going to be doing the same thing. Cool. All right, so let's look at the statements, let's look at the symbols here. I'll make this a little bigger. So this is a tilde, the first one right here is a tilde. Sometimes you might see in computer programming, you might see this symbol here. Both of them mean not. They're for negation. The next symbols go in between logical expressions. This second one means and this one below means or. So they're kind of like in algebra we used, remember, the union symbol and the intersection symbol. Well, in logic we use the V and upside down V pretty much to represent or and respectively. All right? Okay, so given statements P and Q, the sentence that I just wrote is read P and Q and is called the conjunction of P and Q. All right, given statements P and Q again, the sentence that I'm writing now is read P or Q and is called the disjunction of P and Q. In expressions that include the symbol tilde as well as the symbols for and or, the order of operations specifies that this negation, the tilde, the not, is performed first. So let's check it out. If we have something like this here, this is equivalent, it's read not P and Q. Notice the pause there. So if we were putting in parentheses to emphasize what happens first, it would look like this. All right, now let's look at the negation of something in parentheses, a logical statement that's in parentheses. So if we have something like this, where this represents the negation of the conjunction of P and Q. All right. So it turns out that this is logically equivalent and we denote that with 3 horizontal bars that are parallel. Well, duh. If they're horizontal, they'd be parallel. All right, so this is logically equivalent to not P or not Q. So think about it. If we think of an and statement, let's say that Shannon had eggs and bacon for breakfast, right? So we're conjoining the statement that Shannon had bacon for breakfast and Shannon had eggs for breakfast. I think I said it backwards. Anyway, long story short, this ends up being logically equivalent to not P or not Q, because in order for P and Q to be true, right, the conjunction of P and Q to be true, they both have to be true. So if one of them is false, it negates the logical and. All right? So, writing it all together, not P and Q is logically equivalent to not P or not Q. All right. So now let's take a look at this one here. What about the or statement? So what we've written here represents the negation of the disjunction of P and Q and is logically equivalent to not P and not Q. Because for an or statement to be true, only one of the logical expressions needs to be true, just like in sets, all right? So the only way to falsify that statement is if both of them were false. So all together, this is what we've got. The negation of the disjunction of P and Q is logically equivalent to not P and not Q. Good? Awesome. Alrighty. So now let's check out the next set of stuff. In this and most treatments of logic, the symbols for and or are considered co-equal. So this is a little weird. They're co-equal in order of operations. So an expression like this is considered ambiguous. Because if there's, if they're co-equal, then there's no working, from left to right, once you're on the same level, like with addition, then you're going to have to choose groupings, all right? So when you're creating these expressions, what you're going to want to do is either write it as P and Q or R, or you'd write it as P and Q or R. Generally, the word but in English translates the same as and when it links two independent clauses. So let's check it out. Charles is a student, but Charles has a car. Would you agree that those are independent statements? One statement does not depend on the other. And so we can read that as Charles is a student and Charles has a car, right? So if we were to let P denote Charles is a student, and if we let Q denote what? Charles has a car then if we wrote this in the common form, what would it be? Well, we would have, good, P and Q. That would be our logical expression. Okay. You also get an and statement with neither nor. So that means not P and not Q. So if we say something like, neither Rory nor Lee have been to Japan, you could rewrite that as Rory has not been to Japan and Lee has not been to Japan. So if we were to let P denote, now what we would do is let P denote the positive. So let P denote Rory has been to Japan. And if we let Q denote Lee has been to Japan, then the way we would write this would be not P and not Q. All right? Cool? Awesome. All right, so now let's take a look at example 2. We want to write each of these sentences symbolically, letting P denote math 226 is easy and Q denote math 226 is fun. So the math 226 at my school is discrete math. All right, so math at 226 is difficult, but it is fun. Well, isn't difficult the negation of easy? Right? You could think of it that way in the English language. So I'm saying that this one would be not P, right? We have a but statement, so we would have the logical and then the last statement is saying it is fun, so it would just be Q. So not P and Q. The next statement or sentence, if you will, because we're not talking about the truth or falsity of anything. There could be differing opinions on this one. But what we would look at is here, so math 226 is neither easy nor fun. So this is negating both statements. So we would have not P and not Q. All right? Alrighty then. So now let's take a look at some more symbols, your favorite. So here, this is a bit of a review. If you have X less than or equal to A, what does that mean? I mean, doesn't that mean that X is less than A or X good is equal to A? And then this other statement here is basically saying that X is between A and B inclusive. So that means what? It means that A would have to be less than or equal to X, and X would have to be less than or equal to B. So suppose X is some particular real number. We want to write each of the sentences symbolically, letting P denote -2 is less than X, Q denote X is less than 1, and R denotes X equals -2. So if we want to say that X is between -2 and 1, then what would we have? This means what? -2 is less than X, and beautiful, X is less than 1. So what statements do those two expressions correspond to here? Beautiful. We would have P and Q. Groovy? Awesome. Next up, -2 is less than or equal to X. Well, this one, remember, was an or statement. So that would be -2 would be less than X, or -2 equals X, right? So, what do you think? Isn't this statement the same as X equals -2? Beautiful. So, our expression would be good. P represents -2 less than X, and R represents X equals -2, and it's an or statement. So you'd put the logical or. Very good. So, -2 less than or equal to X less than 1. Well, what does that mean? That means that first we would take care of, well, let's take a look at it like this. So -2 has to be less than or equal to X, and X has to be less than 1. But don't we need to work on this guy a little bit? Didn't that mean we just did that, right, from number 2? I mean, this was P or R, wasn't it? And that would have to be taken care of first. So we would end up with P or R. We would group that, and then and great, Q, because this one is Q. Good so far? Let me go ahead and box the final results of these because I want you to see the end result. Awesome. Now we get into something that's kind of fun. It might look a little bit intimidating because you end up making lots of charts, but it's really kind of cool. So, first definition, if P is a statement variable, the negation of P is not P, or you can read it as it is not the case that P. And actually, my evil plan was to write this in words, not P, and it's denoted with the tilde, not P. It has opposite truth value than P. If P is true, not P has to be what? False, because in order for you to have a statement, it can only be one or the other, right? So if P is false, then not P therefore must be true. Beautiful. So the truth values in a chart, this is kind of what we just wrote. So if we take a look over here, if P is true, not P is false. If P is false, not P is true. Good so far? Now, another thing to look at is that P, if you take a look and think about, is P logically equivalent to not P? Do you see that it wouldn't work out because these truth values would have to be the same, right? So going horizontally, you would have to have the same values for a logical equivalence. But we'll get to that soon. All right, so moving right along. Building it up, if P and Q are statement variables, the conjunction of P and Q is read P and Q, and it is denoted good with that logical and statement in between the P and the Q. It is true when and only when both of these guys are true, right? If either P or Q is false, or if both are false, then P and Q is false. All right, well, if P is true and Q is true, then the conjunction of P and Q is true. And by the way, this is kind of the typical order that people go in. They start out with the P, both of them being true, and then they keep the leftmost one true and make the next one false. So that would make the conjunction of P and Q false. Then you go into the case where you'd have a false true. P is false, Q is true. That would make the conjunction false. And then if they're both false, the conjunction is also false. Cool, cool? And what we're going to do is use these truth values in order to see if something is logically equivalent. That's where we're headed. Okay, so now, here we go. If P and Q are statement variables, the disjunction, yes, you want to know these words and definitions, of P and Q is P or Q and is denoted with the logical or symbol. It is true when either P is true or Q is true or both are true. And it's only false when both P and Q are false. Okay? So let's check it out. Again, we'll start out with true, true. So P or Q would be true. If you go to true, false, well, just needs to be one of them true, right? So that's still true, the disjunction. Again, we go to false, true, you'll have a true, but if they're both false, then the disjunction is false. All right, so now we move on to evaluating the truth of more general compound statements. A statement form is an expression made up of statement variables and logical connectives. So the logical and, the logical or, the not, those were all logical connectives. Kind of go off to the side. All of these were logical connectives. All right, so statement form is an expression made up of statement variables and logical connectives that becomes a statement when actual statements are actually substituted for the component statement variables. The truth table for a given statement form displays the truth values that correspond to all possible combinations of truth values for all component statement variables. All right? So it's easier shown than than explained just verbally. So let's check it out. All right. So we've got something that's called the exclusive or. By the way, the exclusive or is denoted in different ways. Sometimes you'll see it like this. Right? Sometimes you'll see it like this. We'll leave it in the logic formats to work with it. And now we need to make ourselves a table, all right, with all possible combinations. Now let's make a table with all possible combinations of truth values, all right, for the compound statement variables. All right, so let's start out by just listing. We've got P and Q in general, right? Well, we're going to need a P or Q, a P and Q, and then we need to negate the P and Q. We need to negate that conjunction. So I'm going to go like this, P or Q, P and Q, and then the not P and Q. And then I think we'll have pretty much everything. So what you do is this. Here's our starters, okay? We're going to basically do one more line over here, or one more entry. My ability to make the straight lines is all due to one of my former students named Courtney. She gave me lots of tips about Notability, which is the program I'm using for annotations. All right, so do you see how we have the setup for everything we're going to need, right? Everything we're going to be using. So now let's go ahead and let's take a look at the end of the day, right? We want that end statement, which is the disjunction of P and Q and the negation of the conjunction of P and Q. All right. So now we'll just do our truth values. All right. So with P and Q, you're getting more used to this now, I believe. Whoops. Here we go. Sorry. Starting out with both true, right? And then a true false, a false true, and then both of them false. Good so far? So actually, I won't need all of that space. Maybe what I'll do is redo those vertical lines. All right. All right, so continuing on our truth values. So we're basically doing one big table. So we've done the P or Q, right? The disjunction of P and Q before, and the conjunction of P and Q before. So remember that we're going to have when the disjunction of P and Q is true all the time except when they're both false, if you're dealing with two variables. So this is a situation for the disjunction of P and Q. The conjunction of P and Q is only true when both P and Q are true, and the rest of the time it's false. Groovy? Awesome. So now to negate that, right, all we would do is put the negation of the truth value. Good so far? Awesome. You guys are doing great. So now, here we go. In order to look at this final statement here, we want to examine the truth values for the disjunction of P and Q and the negation of the conjunction of P and Q. So we're going to look at these. We are also going to apply the logical and, right? This guy here. So remember when you have we're basically doing the conjunction of the expressions that I circled. And remember, the conjunction is only true when if you have two expressions, if they're both true. So this first one, would be false. We'd have a true and a true, so the second would be true. True and a true, and then false and true would be false. Right? Groovy? So that's it. That's the truth table. So you know which ones are true and which ones are false. All right. So let's take a look at this one here. We now have three variables. So check this out. This is kind of like a binomial situation where if you've got these statement variables, right? What those are like your P, Q, etc., PQR. Well, notice when you had P and Q, what kind of situation did you have? You had four possible situations, right? Or 2 squared. When you just had P, you had two possible situations, true or false. So you had 2. So like 2 to the 1, 2 to the 2. How many situations do you think you'll have if you have 3 statement variables? Beautiful. 2 cubed or 8. Very good. So that kind of gives you a heads up for how big you need to make your truth table, right? So here we're going to have, we need P, Q, and R. We need the disjunction of not Q and R. So here, what we want to do is we're going to need a not Q, right? And then we'll do not Q or R, right? Or the disjunction of the negation of Q and R. And then remember that at the end of the day, we write the entire statement. So you'd have the conjunction of P and the disjunction of not Q and R. Cool, cool? All right, so we're going to need to make this table a little bit bigger. By the way, if you're looking for an annotation program, this really is a great one. I really like Notability. I'm just going to go ahead and take it down here. And you can literally go like this, and then it'll connect the dots for you. All right, and then here we go. Going across here. All right, so why don't you go ahead and pause the movie and try doing these truth tables on your lonesome, and then go ahead and tune back in and check with me to see how you did. All right, let's check it out and see how you did. So let's start out with all of these P, Q, and R being true, all right? And then what we're going to do is work in a false starting from the right. So if we kind of work this false throughout, where two are true and one is false, we'll have the next statement be true, false, true, right? So that gave us one false, all right? No. Okay, let's see how you did. Let's start out with true, 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 right? Now let's let one of them be false at a time. So that would leave us with true, true, false, and true, false, true. Now let's move into the case where P is still true, but the others are false, right? So we've basically looked at every situation where P is true. That make sense? All right, now let's start the situation where P is false, right? And the others are true. Then, again, P is still false, and then we need one false worked in there. There's two cases where that can happen. And then the very last case is when all of them are false. Good so far? Awesome. Now, if we take a look at not Q. So to ascertain that, we're just taking a look at the truth values that are under Q, and we're going to negate them. So we would end up with false, false, true, true, false, false, true, true. So again, I was looking at this column here, right, in order to find out what not Q is. Groovy? Alrighty. So now, moving over to not the disjunction of not Q and R would be what? Good. You get a true statement all the time except for when both of the statement variables are false. So the only time, let's see, so now we're going to take a look at the R and the not Q. So we're going to end up getting true statement, false statement, true, 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 false, true, and true. So for this one here, this one here, right? What did we look at? We looked at these two columns. Groovy? All right. And next up, we just have our kind of end of the day statement, right? So for this guy, we need to look at P and then this column that we just completed. Now this is the conjunction of those two, so it's only going to be true when both are true. So I have a true and a true. I get a true. True and a false is false. True and a true is true. And then true, false, 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 and false. And then easy way to double check that is to look only where they're both true. Yep, so we're good. Cool, cool? All right, so now we get to logical equivalence. So like I was saying before, these truth tables are going to be a tool for us to find out if we have logically equivalent statement forms. All right, so two statement forms are called logically equivalent if and only if they have identical truth values for each possible substitution of statements for their statement variables. The logical equivalence of statement forms P and Q, those are statement variables, so we do a capital when we do statement forms. That's denoted by writing P with those lines again. So this here means P is logically equivalent to Q. Now, two statements are called logically equivalent if and only if they have logically equivalent forms. When identical component statement variables are used to replace identical component statements. So again, let's learn by doing on this guy. So example 4, determine whether the following statement forms are logically equivalent. Please construct a truth table and include a sentence justifying your answer. So here we go. Again, we got to think of all the situations, right? But at the end, there's going to be a comparison. So remember before in the previous columns, this was kind of right here. I mean, this was our end result, right? We figured out when, these things were true. So next up, what's going to happen is we're going to have a comparison. And as long as they're the same, then they're logically equivalent. But if they're not, which is fine. All right, so let's do it. So if we have we just have P and Q as statement variables, and then we have a variety of stuff we need to find. But let's start out by saying, is the color I was using? Yep. Let's start out by having our P and our Q. So then that means that it's just going to be, we have 2 statement variables, so that's going to be just 2 squared, so 4 possibilities, right? So our table doesn't need to be that long here, but it might be a little bit wide. I don't know. Let's see. So if we come over here and we start writing what we need to find, we need to find we're going to need to find P, the conjunction of P and Q, right? We're going to need to find actually, let's just start with the negations because we'll need those. So we'll need not P, not Q. We'll need the conjunction of P and Q. And we're going to need the conjunction of not P and not Q. And that's our setup. And then we do our comparison, right? So actually, I'm going to need, let's put this one first. We're going to need the negation of the conjunction. And we're going to need the what? The conjunction of not P and not Q. So those are the things that we want to compare at the end. And so we have everything set up that we need. All right. So notice at the very end, I have what we're comparing, right? And so if all the truth values are the same in the last box, then these 2 statement forms will be logically equivalent. And if not, they won't be. So let's do it. And actually, if you want to pause the movie, that would be awesome. Try it yourself. Struggle a little bit. Practice a little bit. And then come back and see what I did. Okay, so hopefully everything went well with your chart. Now, if you take a look here, we're good at the beginning. Both of them are false. And at the very end, both of them are true. But do you see that these guys have different truth values, right? So at the end of the day, negation of the conjunction of P and Q is not logically equivalent to the conjunction of not P and not Q. All right, which is a common mistake. People try to say that's equivalent. All right. Now let's look at the second one. The negation of the disjunction of P and Q. We want to compare to see if that's logically equivalent to the conjunction of not P and not Q. So again, it's going to be a real similar chart. Try it yourself. I'm going to move a little faster and check with me at the end and see how you did. Okay, so notice that all these truth values are the same, right? So what does that mean? That means that we found out that the negation of the disjunction of P and Q is logically equivalent to the conjunction of not P and Q, not Q. Right? So, just like in algebra, when you're trying to simplify algebraic expressions or, solve equations, you utilize all of these kind of properties, right? Well, this is, useful equivalences in logic land. All right, so this also happens to be one of De Morgan's laws, which are used a lot. I've been consulting with one of our professors who teaches computer science, and so he said, make sure they know De Morgan's laws, all right? And speaking of which, De Morgan's laws are as follows. The negation of an and statement, a conjunction, is logically equivalent to the or statement in which each component is negated. So, using symbols, remember we've got the negation of the conjunction of P and Q is logically equivalent to the disjunction of not P and not Q. All right, so the negation of an or statement is logically equivalent to the and statement in which each component is negated. So that is the one we had just done. So the negation of the disjunction of P and Q is logically equivalent to the conjunction of not P and not Q. Cool? All right, well, let's take a look at a situation, right? So let's say X is some real number, right? So X belongs to the reals that funny looking E is an element of, belongs to. And let's also say that, I don't know, why don't we say that 0 is less than or equal to X is less than 3, I don't know. When we look at what this actually represents, right? Making this picture, it means that X is between 0 and 3, including 0, right? So we'll just do it with a closed circle, right? And then an open circle. So it'd be every number, in between 0 and 3 where 0 is included. Right? let's explore this further, right? This is saying here that 0 is less than or equal to x, and x is less than 3. Well, if we let this be a p and if we let this be a q, wouldn't, in logical land, wouldn't this be the conjunction of p and q? Well, what if we wanted to negate that, right? Well, using a picture, right, we know it's got to be everything else, right? So if we came over here and we looked at negating it, now the 0 would be an open circle, the 3 would be a closed circle, and we'd want the tails, wouldn't we? We'd want those tails because we don't want the stuff that was included. The negation would be everything else, right? So, okay, well, so this is the negation of 0 less than or equal to x less than 3. So what would that mean? That would mean that 0 we would not want that to be less than or equal to x, right? What else would we have? We would have, or we wouldn't want x to be less than 3, right? Well, isn't this not p? This is not q. And so we would have not p or not q. Isn't that kind of groovy? Right? So that's sort of an illustration of one of De Morgan's laws. All right? And that is actually the first one, right? The first Morgan's law kind of illustrated. De Morgan's law illustrated. Okay, so tautologies and contradictions. A tautology denoted T, it's a bold T and typeface, is a statement form that is always true regardless of the truth values of the individual statements substituted for its statement variables. A statement whose form is a tautology is a tautological statement. Now, a contradiction is a statement form that's always false. Regardless of the truth values of the individual statements substituted for its statement variables. A statement whose form is a contradiction is a contradictory statement. Okay, so let's take a look at the next example. So for example 5, we want to do the same thing pretty much as example 4, but now we've got this tautology business and contradiction business. So let's do it, all right? It's a little bit simplified in that a tautology is always true, right? So we're only going to need 2 rows because the tautology is always true. So there's only one situation for that. So we're only looking at how the values P can take on as far as true or false. Not values, but whether P is true or whether P is false. So we have P, I'll kind of try to make this bolded, and then our tautology T. And we want to see if we've got logical equivalences between the conjunction of P and T and P alone, all right? So, and we'll just write this over here, and I'll rewrite P so we have it. All right, so here we go. So P can take on the values of true or false. T is always true, no matter what. And remember, when you conjoin two statement expressions, or two logical expressions, what you're going to have is, or when you conjoin two logical variables, what you need to do is have everything be true. So this is a situation, true, false. Remember, P could take on true or false. So they've got the same truth values, right, in their truth table. So what can we say? We can say, beautiful. We can say that the conjunction of P and T is logically equivalent to P. Now, the conjunction of P and a contradiction, right? So let's set up what we're going to need, P, C. So then we'll need the conjunction of P and C, and then we're going to need the disjunction of P and C. All right, so working it out. Again, P can be true or false. A contradiction is always false, right? And so do you see that the conjunction of P and C can never be true? It's always got to be false because they're never both true. But the disjunction of P and C, right, is true if one of them is true. So what do you think? Do you see that here you've got different truth values on the first row in comparison? So therefore we can say what? That the conjunction of P and C is not logically equivalent, right, to the disjunction of P and C. All right? So here we go. Summary of logical equivalences. If you go back to the truth tables, you can see why these are equivalent. You can always do truth tables in order to prove to yourself that these are equivalent. In fact, that would be a real useful exercise. But we're just going to go ahead and give you a list. We haven't really talked about every single thing here, I don't think. We left out a couple of them, but these are useful for you, and these are the names of them. So commutative laws. It turns out that the conjunction of P and Q is logically equivalent to the conjunction of Q and P, right? And the same works for the disjunction. So the disjunction of P and Q is logically equivalent to the disjunction of Q and P. So now if you've got, 3 of these statement variables like P, Q, and R, right? And the same operation is between them. So this one is the conjunction, right? Remember, you've got to do 2 at a time or it doesn't make sense. But it turns out that it doesn't matter, as long as you don't rewrite them, it doesn't matter which 2. So here I grouped the conjunction of P and Q first, and then you can join that with R. Or you could say you could conjoin P with the conjunction of Q and R. And then again, if you've got the disjunction, it'll work the same all the way through. So again, P, Q, and R, P, Q, and R. You've got this, same operation in between them. But remember, you've got to group them. So if you go the disjunction of P and Q first, and then the disjunction of P and Q and then R, that's going to be logically equivalent to the disjunction of P and the disjunction of Q and R. It's a mouthful, isn't it? Okay, distributive laws. If you have this situation where you're conjoining P with the disjunction of Q and R, it turns out that that's logically equivalent to the disjunction of the conjunction of P and Q and P and R. And similarly, if you've got the disjunction of the conjunction of Q and R, disjunction of P and the conjunction of Q and R, that's logically equivalent to the conjunction of the disjunctions. So you'd have P or Q and P or R. Okay? All right, identity laws. So here you would use your tautology, right? That's like your identity element here. So the conjunction of P with a tautology is going to be P. We showed that one. And the disjunction of P with a contradiction is logically equivalent to P. The negation laws would be the disjunction of P and not P is logically equivalent to T, and the conjunction of P and not P is logically equivalent to a contradiction because it can't ever be true. All right, double negative law, right? If you've got the negation of P, that's logically equivalent to P. And then there's nothing that's supposed to be in this box. And then idempotent laws, right? So it turns out that the conjunction of P with itself is logically equivalent to P. And the disjunction of P with itself is logically equivalent to P. Universal bound laws. So the disjunction of P and T is logically equivalent to T. And what do we have over here? the conjunction of P and C is logically equivalent to C. We talked about De Morgan's laws. So if you're negating a conjunction, that's logically equivalent to the disjunction of the negations. Oops. The second De Morgan's law, remember, is that if you negate an or statement or a disjunction, that's logically equivalent to this and statement here, not P and not Q. So the negation of a disjunction is the conjunction of the not P and not Q. All right, absorption laws. All right, so if you have P or P and Q, turns out that's logically equivalent to P. That'll be useful and proofs. And if you have, sorry, must be the mailman, poor soul there. If you have P and P or Q, it turns out that that's logically equivalent to P. And negations of T and C, not true all the time, is logically equivalent to a contradiction, and not a contradiction all the time is logically equivalent to a tautology. Thank you for tuning in. Hey, if you liked this video, please subscribe and let me know what other types of videos you'd like to see.